Hi everyone, let's go over some other example how to make this simplex. Now I'm going to try an example a little more simple, and I will show the example in this simplex and also how does this translate into the graph. Okay, so let's see first. This is the problem. So I want to maximize z, and z is equal to 2x plus a y, and it's subject to 3x plus 2y that has to be less or equal than 2, and 4x plus y that has to be less or equal than 2 also. So here is the graph for this problem. So here are the two constraints graphed, and now I'm going to add our objective function, our isoprofit line, so we can see what's the maximum value. What's the maximum value of this function? Okay. Okay, makes more sense. Here is the isoprofit line, and we can see that this is going to be optimal in this point over here when the two constraints intersect. So it's not when the constraints intersect with the axis, but it's in this little point over here. So now we know what the optimal is, and let's begin to think how this can be translated to our simplex algorithm tables. So first, we have to change this problem to the standard form. So it's like z minus 2x minus y. And the constraints are going to be 3x plus 2y plus a select variable. It's going to be equal to 2. And then the other one, we have also to transform in an equality. So it's going to be 4x plus y plus the second select variable, and it's going to be equal to 1. Now we can put that data into the table. So here in Z, it's going to be on the first line, the first row. And what I'm going to do is assign X and Y as a non-basic variable. So it's going to be 0. So X equal to 0, it's a non-basic variable, and Y it's going to be equal to 0. Why do I do this? Because I need to find a feasible solution. And a trivial feasible solution is when the x, y, and the y is going to be 0. So I'm certain that this will be in the feasible area in this problem. So that's a trivial solution, and I will preferably start with that. But when I put x and y as to 0, my slacks will have to have a value. So these two equalities will make sense. And the values that they have are going to be 2 and 2, right? Because both x and both y and i's are 0. So here our basic variables are going to be s1, and it's going to be the value of 2, and s2 that's going to have the value of 2. In this case, when both x and y are 0, of course the z is also 0. So Let's go back to the Tableau. We have the Z, and the X is going to be 2 minus 2, right? Because it's here. The Y minus 1. The S is going to be 0 because it has none here in the objective function, and that's 2 also. Now, right hand side is going to be 0 because that's our Z. In the row 1, we're going to put the constraint, the first constraint. So it's going to be the coefficients of each variable. It's going to be 3, x, 2, y, and 1 as 1, and 0 as 2. This, and of course, the right-hand side is 2. And then the second constraint is row 2. It's going to be 4, 1, and 0, of course, and 1 as S2. And of course, the right-hand side too. So that's our initial tableau. And that's what it means, every value that it's here. So one thing that we can also make an analysis of is that all basic variables have to have this format. So we have one row as 1 and the other ones in the same column as 0. That's one way we know that this is basis. This is inside the base. So we know that our basic variable over here again is going to be S1, and this one is going to be S2. And in the graph, what that means is that now we are here in this region here, and we need to find where are we going to look into another basic feasible solution. Where in this space of feasible solutions am I going first? And to make the decision, we choose always the variable that is going to contribute more for the objective function. And in this case, it's going to be the x. So if I add the x to my problem, I will reach faster my optimal solution because it's making a bigger contribution to the objective function. And a practical way of saying this is choosing always the most negative number in the row 0. So in this case, we just choose the pivot column, and now we have to choose the pivot row so we can find our pivot number. And for us to make this, we have to divide the right-hand side to the number in the same row and in the column of the variable that we want to increase. Doing that, we find that the smallest number, positive number, it's going to be in the row 2. It's going to be the division of the right-hand side with the 4 of the x column. And what that means is that the limit for me to grow x, it's going to be given by this constraint. And what happens here is like, if I want to grow x and y, it's small, it's 0, and S2 has some value, I will decrease S2 and increase x to an amount. And the maximum amount that I can increase this is going to be half, right? Because it's going to be for x equal to 2. And here, if all the other variables are 0, this one I can increase by 0.66, 2/3. So it's the one that's limiting my increase in x, it's the second constraint. So that's why I'm going to use the second constraint as the constraint for me to make this operation. And now what we have to do is make the elementary row operations in order to enter back to the base and take off the S2 from the base. So for us to do this, we have to bring the value in the pivot number to 1 and the other two to 0. For us to do this, first we have to, let me just copy here, it'll be easier. Okay, I can just divide this for 4, right? So it's going to be row 2 divided by 4. And with 3, I can divide R2 by 4, minus 4, and sum to row 1. Of course not. Okay, so I can multiply R2, that is always our pivot row that we are going to make any multiplication or division. And so I can multiply by 3/4 and negative 3/4 and sum to our row 1. So that's what we did here when we got the value in the row 2. We multiply by minus 3/4 and we sum to the row 1. Now we have 0. And we do that not only with the column X, but with all the other columns. The same thing here and there. It's the same operation. Now for the last one, we can divide this row 2 by 2 and sum to the row 0. So it's row 2 divided by 2 plus row 0. So let's see. Row 2 divided by 2 plus row 0. That's perfect. So now I have a different table. Now I have a different table that with different bases, because I enter x to the bases and I took off and I left S2 of the bases. So now, and also I went a little further from where I was here at the start. So I went a little further and now I have a Z value. So now my non-basic variables are going to continue to be y equals to 0, but now it's S2 that leave the bases. So S2 is 0. And how do I know that? Looking at this is because S2 now doesn't have that standard form. It has a different form. So it means that this variable is not in the base. And our basic variables are going to be x, that it's going to be half, and S2, and S1, that it's going to be also half. And we can see here that it does make sense. Now z, sorry, now z is 1. So I now have half x. So I have the z value as 1. And that's what we did here. We went here. We decided to increase x and decrease the surplus 2. Oh, sorry, the slack 2. Now we are going to make this movement over here because we are still not in the optimal. We are here. This place here is our optimal. So what the simplex is going to do is try to look for this point over here. And how it does this is showing us that we can still add something in the y variable, putting this number here as a negative number. So now we have that this is our pivot column. And now we have to find, with using the ratio test again, which row is our pivot row. And the same thing we're going to do, we are going to divide the right-hand side with the appropriate value in the y column. And choose the smallest positive number to be our row, our pivot row. And this here are going to be our pivot number. So this is 1 1/4, or 5/4. So for us to transform this in 1, as we should, to make our row operations, we have to multiply this. We will have to multiply this value by 4/5. So now it's run like we wanted it. So R1 multiplied by 4/5 is the operation that we need to do to all the numbers in this row. Okay, now for this one, we'll have R1 multiplied by 4/10 or 2/5 plus the R0. Let's see if it's going to work. I have this value here multiplied by 4/10 plus the R0, and it's 0. Perfect. Now for this other operation here, I can do a similar thing, right? But it's going to be 20 here, and it's going to be negative. Of course, I can simplify this, but for now I don't need to. So minus 420, since I'm doing this in the computer, using the computer. Now this. They always make all the operations first in the row 1. That's our pivot row. And then just add the row that you want to modify. What's happened? Okay. Perfect, 0. Now, what happened is that I added my y and replaced the y with the S1. So now my non-basic variables are S2 and S1, because I replaced the y with S1. And so the S1 is going to be out of here, and it's going to be replaced by y. And the x is going to remain as my basis. So my basic variables are going to be x and y, and my non-basic variable are going to be s1 and s1, s2 and s1. Now for the values. Now I don't have anything here in the row 0 that is negative. So that means that I've reached my optimal. So this value over here in the right-hand side that indicates the z value is going to be my optimal value. So 1.2 is my optimal value. And the values for x and y, they are the basic variables, are going to be 0.4 and 0.4. So if we replace these numbers over there in our objective function, we will find that 0.8 plus 0.4, that it's the z value that we found over here in the tableau, 1.2. So that's an indication of what we have done is correct. But we also can see here that's exactly the value that we found in the graph solution, the graphical solution. So it's 0.4 and 0.4. So that's how you do the simplex algorithm. And that's what represents each step of the way. And we can see exactly the values that it is showing us, and also the movement that it's making through the feasible space. How he's looking, how the algorithm is looking for those basic feasible solutions to try to find the optimal solution for our problem, right? So that's it.